Howdy everybody, Mr. Mark with you in the Physics Funhouse, and let us go through and analyze our data that we collected in the first video on our Hooke's Law lab. So here's my data table with the masses that we hung from that spring and the distance that that spring stretched each time. And then over here I've gone and filled in most of the forces, but I left the last one blank there. So double check your numbers and make sure that they kind of match mine there. The reason why that last one is blank, it is a good habit in physics whenever you are doing work that you're going to turn into me or show to somebody else, that you don't just write down these numbers that you calculated, but that you show somewhere, somehow, how you calculated those numbers. So what we would do maybe in a section under our data table is show a section for calculations. Now this is a real simple calculation, but it's still important that you show everything that you do. Don't leave me to assume something you do, make it clear and evident. So when we calculated that force, again, the way that we do that is we multiply the mass in kilograms by the gravitational field strength on Earth, which is given the symbol G. So write out your equation that you're going to use first, then clearly show your substitution. I used the wrong color for my M there. Meant to use this color. So when you show your substitution, make sure you substitute in the correct unit. Remember, we wanted the mass to be in kilograms. And so 1,000 grams is equal to 1 kilogram. So whenever we substitute in numbers, we want to make sure we also substitute in the unit, and that helps us make sure, number one, we're using the correct value, and then number two, that whoever's reading our work understands what we're doing. And so the value of G is 9.8 newtons per kilogram, but for the purposes of today's lab, we're going to round that off to 10 newtons per kilogram and show your units there. And then you can show how the kilogram cancels out. There's a kilogram on top, one on bottom. You can show how that cancels out if you like, and that would give you 1 times 10 is 10, a force of 10 newtons. So show that one time. It doesn't have to be for any particular value in your data table, but show the calculations that you do anytime you do a calculation, but just show one sample. So I'm going to go ahead and put that here in my data table, and now my data table is complete. Our next job now is to create a graph of stretch versus force. And so in order to do that, we're going to need a sheet of graph paper. We want to take up the whole sheet of graph paper. Now, how you turn your piece of graph paper, it kind of sort of depends on the situation that you're graphing. I'm going to turn mine landscape style because then it fills up most of the video camera and you can see it a little bit better. The other reason why I would do that is because the numbers on my y-axis are a little bit nicer than the numbers on my x-axis. Force is going to go on our y-axis today, and it's got numbers like 2, 4, 5, and 6. Those are easy numbers to manipulate and count by. The stretches aren't as easy, so I'm going to put those on the horizontal side of the paper, on the long side of the paper, excuse me, where I've got some more room. So to set up axes on a piece of graph paper, we're not going to start just right over here on the edge. We're going to come in a little bit, and like one ruler width is usually a good idea. And so carefully draw you a y-axis. In this case, I don't need to do any negative numbers, and so my origin is going to be kind of down here in the bottom right-hand corner. And same thing about moving up from the bottom. Move up a couple of spaces from the bottom. I mean, it doesn't have to be perfect, but you do want to leave some room to write underneath your axes. And then draw it like that. So again, we're going to put force on the y-axis. Make sure we label it. So up here at the top, I'm going to write force, And then with everything that we do, we need to include units. And so instead of having to write out the units here, I'm just going to put the units with the label. So force is in newtons, and then our stretch is going to be in centimeters on our x-axis. So your next job then is to figure out, well, how am I going to use these lines to fit the data on here? And one common trick that you can do is kind of just count the number of lines that you've got, figure out your data range. Like on my force axis, I need to go from 0 to 10, because we do want this to still be 0, 0. We don't want to skip around. That's going to make it confusing to understand what our y-intercept means. So I'm just going to think about this like I need to go 0 to 10. So one thing you can do is count how many lines you got over here, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So approximately 30 lines. And then divide that range by the data range that you have. So like 30 divided by 10 would be 3. And so one option would be to make each line worth 3. So go 3, 6, 9, etc., etc. I don't know about you, but counting by threes is not intuitive for me. And so maybe bring that down to a number you can count by. Like for instance 2. I think 2 would be an okay thing here to do. And so if I counted up by 2, or excuse me, every 2 lines, I think I kind of said that backwards. So make that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, kind of like that. And if you want to, go above that, you can, but you don't necessarily have to. So the key that you have to look at when this is all done, and that there are some intuitive ways to kind of figure out a scale. If your scale doesn't go at least halfway up your axes, then you could just double your scale and do that. And so that's kind of your rule of thumb to follow there. If you're not at least taking up half the space with your scale, just double it, and then you will take up more of the space. So on my y-axis, that's a little bit kind of fuzzier, because, excuse me, my x-axis. My x-axis numbers go from 40 to 78, approximately. Now, I'm not going to start my x-axis at 40. I'm still going to start my x-axis at 0. In fact, let's go ahead and write that this is 0 right there. And so what that means is that my data is going to kind of sort of be over here, and I'm okay with that. One thing we want to do is extrapolate backwards. Well, what would 0 look like? And so it's important that we don't do that little trick that they do sometimes in economics and population models and stuff, where we draw a squiggly line and then we skip most of the numbers. We need to, almost always in physics, include 0, 0 in our graph and our axes. And so this needs to go more or less from 0 to 80 is kind of how I'm thinking about it. And so if you kind of count the number of lines you've got, 20. I've got about 40 lines to work with. And so a scale of every other line being, or excuse me, every line being worth 2 would probably work out well for my x-axis. And so I'm going to start off with this being 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. And by the way, it is not necessary to label every single line like I am doing right now. In fact, it would probably be better if you labeled every other one or just the tens or whatever. I'm just doing my best to be as clear as possible and not make any mistakes. Because one thing that happens to students when they start graphing, they find a point and they come down, and then that point doesn't have a number right there. That line doesn't have a number, and they just look at the one next to it. And sometimes they just make simple transcription errors like that. All right, so now I'm out to 80. Okay. So you're always going to write with a pencil. I'm writing with a marker so that you guys can see what I'm doing. Go back and just double check when you have a long stretch like that. All right, so now we're ready to put some dots on our paper. And so we're going to go back here. So here's our x-axis. Forces are our y-axis. So this is just an xy ordered pair thing, just like in pre-algebra. So I'm going to go to 46.9, and a ruler is helpful for doing these things. So there's 46.9, a little bit further than halfway in between the two lines. And then a force of 2 newtons. And so just go up to 2, put your dot. A stretch of 54.6, so not quite halfway, and then 4, be like right there. Then 58.7, be a little bit more than halfway, and a force of 5 newtons. And then so on and so forth. So we're just going to plot our data, and we're going to plot them as real nice, neat, little tiny dots. And in the interest of time, I'm not going to do all of them. Let me go and do at least some at the very end. So I've got 78.3. By the way, the order of an ordered pair doesn't matter. Like, it doesn't matter the fact that we didn't have a pattern to the masses we did. Because as long as it fits a trend, the dots are useful. And so if these were the only 4 data points that I did, that's fine. I can still make a line from that. And so the fact that I didn't do one at 100 or 300, but then I went for 400 and 500, that doesn't matter at all. All I want is dots on my graph that I can then use to draw a best fit line. Let me put one more on here. You're going to put all the dots on there. I'm going to do just one more for the purposes of moving quickly. So I'm going to do 70.6. It's about right there. About 800. Okay. So what you'll notice is that your dots should make something of a straight line. I think I may have messed up that one point at the end. Let me double check this. So 78, I got my ruler messed up. 78.3, and then 10. I'm so sorry, y'all. All right, so that's erased right there. And this is why you would use pencil. You can see how easy it is to make mistakes. Or maybe I made that mistake on purpose to illustrate why it's important to use a pencil, and it's real easy to make mistakes. Okay, now next thing, and this is the most important thing, is we're going to draw a best fit line. Now a best fit line is a line that's going to line up with the dots, and my dots line up pretty nicely. If you look at that, those things all kind of sort of fall right along the ruler when I lay it like that. Kind of manipulate it a little bit. The goal is to get the same number of dots above and below your best fit line. Now that doesn't mean turn it like this and go, okay, I got 3 over here, 3 over here. That's not what I mean. What I mean is manipulate it along that line until you've got about the same number above as below. So that's pretty good right there. If you notice that you have dots over here that are above your ruler and dots over here that are below your ruler, you would just turn your ruler to line them up a little bit better. And so the first time you do this, do it lightly with your pencil. And then just draw carefully your best fit line. Now your best fit line should extend all the way to the edges of your paper, down here and over here, be how you draw your best fit line. The next thing that we're going to do is we're going to calculate the slope of that best fit line. Now the way that you calculate the slope of a best fit line is by doing y2 minus y1 over x2 minus x1. You can't go and count boxes like you may have done in pre-algebra because these boxes they're not squares. The scale over here is not the same as the scale over here, so that's not going to work. So what you want to do is find points that actually lie along your best fit line. And by the way, you do want to show your calculations for the slope on your graph. And so I'm just going to say equals 1y minus another, 1x minus another. So let's go get some y's and x's. Inspect your best fit line, look at it real carefully, and hopefully you have some points where the best fit line crosses the grids right where the two little blue lines meet. And so looking at mine, I don't see any where that's true. And so your next move then is to try to find places like right here where the best fit line crosses one line and then like exactly halfway on the other. And so the y coordinate for this point is like 82, 84, 86, 88. Excuse me, that's the x coordinate. 88, and then I'm going to include the units, centimeters. The y coordinate for this point over here, that's 13 and a half. So about 13.5. Nope, 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 nope. That doesn't go there. That goes up here. That's a y coordinate. Just kidding, y'all. Okay, so then we do that with another point that lies along our best fit line. So maybe my best fit line does not match our grid very well at all. So I'm going to use this one right here. So that point's got an x value of 62, so minus 62 centimeters, and a y value of 5.5, 5 3/4, so 5.75. And I'm making all kinds of mistakes. The unit up here is not centimeters, it is newtons. Okay, and I did not bring my calculator back here with me. All right, so now you got numbers. You want to manipulate those numbers and get a single number, so calculator time. So I'm going to come down here, I'm going to do slope equals. Please don't forget your order of operations. Do your top first, do your bottom first, and then divide. Remember that a division sign is like a grouping symbol. And so if you want to think about this as being in parentheses, that would be correct. Parentheses, parentheses. PEMDAS, do your parentheses first. So I'm going to do 13.5 minus 5.75 gives me 7.75. And newtons minus newtons is newtons. And then on bottom, 88 minus 62 gives me 26, so 26 centimeters. For a slope of, now do that division, 7.75 divided by, use the answer key, y'all. It helps with keeping track of your numbers. Gives me a slope of 0. Rounding to the nearest significant figure would be 30, like that. And the unit is Newton, because Newton is on top, over centimeter because centimeter is on bottom. And that is my slope. Now, the slope of a line is important because what we really want to do with this is we want to write an equation like y equals mx plus b. Hopefully that looks familiar from like pre-algebra. And so we're just going to start substituting into here. The y value, that's not a value, that's a variable. And your variable that's on the y-axis is force. And so we can use an F to represent force. Slope, that's m, that's what we just calculated right over here. And so I'm going to write 0.30 newtons per centimeter. And then plus x, or excuse me, times x. The symbol that we can use for stretch is just an x. And so F equals 0.3 newtons per centimeter times x. And then the plus b thing, well, that's our y-intercept. In this particular case, our y-intercept is like way, way, way down here. And so we're going to have to do something a little bit different to figure out our y-intercept. But I can tell that it's going to be a negative number. And so I'm just going to go ahead and put in a minus sign right there. So the way that you can figure out your y-intercept in this case, and I'm going to kind of, my graph is getting a little crowded. Let me do this over here. So if your y-intercept is not apparent on the graph, like if it crosses right here, you can just read it off your graph. But if it happens to be down here, then your y-intercept may need to be calculated instead of just like looking at the graph. And so the way that you do that is you take your y equals mx plus b equation. And so right now it's F equals 0.3 newtons per centimeter times x minus b, and then go ahead and just solve that for b. It's like, well, what is b? And so if you add the b to both sides of your equation, it'd be b plus f equals 0.3 newtons per centimeter times x, and then subtract f from both sides. So b would be 0.3 newtons per centimeter times x minus f. And now I can take those points from my graph and just substitute them in for x and f. So I have a set of x and f, and it doesn't really matter which points you use, like 13.5 for f and 88 centimeters for x. So if I just substitute those in here, and so 88 for an x minus 13.5 newtons for an f, then that will let me calculate what my b is. So again, following your order of operations, be careful. 0.3 times 88 equals 26.4. That's what that part would be. 26.4. And then notice that the centimeters would cancel out. Centimeters on bottom, centimeters on top cancel out. Minus 13.5 newtons. And so then when you subtract that, you get like 12.9. Yep, forget my unit on that. And Newton minus Newton is Newton. And so the y-intercept in our equation is 12.9. So let's go back up here. Minus 12.9. And then it has a unit of newtons, capital N. Okay, so this is our equation. Put a box around that. Notice that your y-intercept has the same unit as your y-axis did, and that should be true. Any number along this line should have a unit of newtons. So the last question that we asked was, what happens if we did a mass of 2? Just put this right here. So what if we had a mass of 2 kilograms, 2,000 grams? So my spring is not long enough. I'll show you here in just a minute. My stand is not tall enough to show you how far it would stretch under a force of 2 newtons. So we're going to be extrapolating this. So one method is to just follow your line until you get to a force of 2 newtons. That's not a very good way to do it. I'd rather you do it with the equation that you got. That's what this thing allows us to do, is to make predictions. So we can solve our equation for a unknown stretch. And so here it's like, all right, take this equation and solve it for x. And so we can do that on here if we wanted to. So F equals 0.3 newtons per centimeter times x. X is what I want to try to find, minus our y-intercept, which is 12.9 newtons. Now, we're going to typically solve physics equations leaving these in terms of symbols, but for right now, it's okay to leave them as numbers. So I'm going to add the 12.9 to both sides. That's F plus 12.9 newtons equals 0.3 newtons per centimeter times x. And then I can divide the 0.3 from both sides. So that would look like F plus 12.9 divided by 0.3 newtons per centimeter is equal to x. And then let's go ahead and substitute in the missing force. Well, we would have to calculate the force that 2 kilograms would exert. And so 2 kilograms times 10 would be 20 newtons. Not sure that you want to do that in your head, but if you need to write it out, you can. And so if I substitute in 20 newtons plus 12.9 newtons over 0.3 newtons per centimeter equals x. Now I can solve and figure out how long the spring would be if I could hang 2 kilograms from it. So 20 plus 12.9 is 32.9. And that is newtons. And then over, still have the 0.3 newtons per centimeter down here equals x. Now dividing 32.9 by 0.3, that's easy. You get 110 essentially. So I'm going to write x equals 110. Now the unit on this one may not be as nice because you've got a fraction and then a fraction within a fraction. And so whenever you have these compound fraction situations, here's what I recommend that you do. And I'm just going to write just the units out here to the side. Instead of writing it as newtons over centimeter, write it as newtons times centimeter to the minus 1 power. That's what over centimeters means. It's to the 1 power, and then minus 1 means I've moved it to the other side of the fraction bar. Well, when you have a negative exponent like that, that just means it's on the wrong side of the fraction bar. So I could also write it like newton times centimeter over newton, because centimeter to the minus 1 is the same as a centimeter on top. And then if I cancel out the newtons, that leaves me with just centimeters. So that means that my spring would stretch 110 centimeters. That's over a meter long. So I don't know if my spring would actually stretch that much. There's a limit to when this line is appropriate and when it starts to break down and the spring reaches its elastic limit. but that's something that we'll talk about later. Real quick, let's talk a little bit about the meaning of this slope, because if I had a different spring, I would still get a straight line, but I would have a different slope. And so the slope in this equation, grab a different color, F equals 0.3 newtons per centimeter times x. The slope is often referred to in this particular physics equation as the spring constant. Which is given a symbol K. K for constant. And so it would be okay for us to write this equation more generally as F equals 0, that's not what I meant to do. F equals just a K times an X. And then for the particular spring that I use, the red spring, the K has a value of 0.3 newtons per centimeter. Which, by the way, the value on the box for the spring constant, because it's made to be a specific spring constant, is 0.25. And so we were just a teensy-weensy tiny little bit off. Me doing this all by myself as far as the measurements go, and then me only graphing a few of the points rather than all of the points led to that little bit of measurement error. So a spring has a specific spring constant, and basically the physical meaning of that number is how stiff it is. So I'm going to say the stiffness. So here in just a second, I'm going to move the camera back over there to the springs and see if we can demonstrate the difference between a red spring and a different color spring, and see springs of different spring stiffness or different spring constant. So I think that's enough for right now. When you finish a graph, it's almost always going to look something like this, where you're going to have y-axis label with unit, x-axis label with unit. You're going to carefully figure out a scale. You're going to carefully plot nice, neat little dots like that. Don't number your dots. That's bad. That's elementary school stuff. Nice, neat, tight little dots. Then you're going to find the slope of that line so that you can write the equation of your best fit line like we did here. And in this case, we were asked to make a prediction using that equation, and so we manipulated it to look something like that. If you had your data table and calculations on the back of this sheet, that is perfectly okay with me. Last thing to mention, you might want to give this a title, and in the absence of any other thing to come up with for a title, you can just